Okay, so we're going to pick up with the 2019 test with number 3 on the AB exam. And I know I keep saying this every time, but this is another really common type of question that you're going to see where instead of given a function, you're given a graph of some sort, and you've got to answer a lot of questions based off of that graph. So on this particular example, number 3 from 2019, we've got a graph of a continuous function f, and it's defined on the closed interval -6 to 5. And that's interesting right away because notice that the graph you have only goes from -2 to 5. So apparently if it goes to -6, that means there's more graph over here somewhere that we're not seeing. So we'll just keep that in mind and see if that comes into play later, which we're sure it will. So it says the figure above shows a portion of the graph, which is what we were just saying, consisting of two line segments, and that's important because it ensures us or assures us that this line and this line are straight lines. There's nothing weird or curved going on there, so we can find the equations of those lines if we need to, or we can find the slopes of those lines. So just knowing that those are straight lines is helpful. And then we have a quarter circle centered at the point 5, 3, which is right here. So that's also helpful. The fact that this is part of a circle is going to help us out later, especially when we're trying to find areas of this graph, which heads up is something you're pretty much always going to have to do on a graph like this. So we know that it is also known that it has the coordinate 3 comma 3 minus the square root of 5. So right here when x equals 3, we know that y value. And that's really helpful because if they hadn't told us what that y value was, we'd be left just guessing or estimating on that. All right, so this is just the setup. They're explaining the graph, the function f, and what we're looking at. So let's move on to part A. All right, so if the integral from -6 to 5 is 7, and if you remember, -6 to 5 was the entire domain, even including the part of the graph that we couldn't see. So the integral of the entire thing is 7. Find the value of -6 to -2, the integral of f of x dx, and show the work that leads to your answer. Okay, so I said earlier we're going to have to find some areas, and that's what I'm showing you right here. So going from left to right, if I were to integrate this function from -2 to -1, for instance, essentially what that would find would be the area trapped in between our function and the x-axis. And notice from -2 to -1, what we have here is a triangle. And so if you want to find the area of that triangle, all you got to do is take your base and your height, which are each 1, so you would do 1 times 1 and then divide that by 2, which gives you 1/2. So the integral from here to here, or alternatively the area under the graph from here to here is positive 1/2. Now notice here I didn't actually type in a number. We know this area is the same as this area. The only difference is that since your graph is below the x-axis right here, if you were to integrate from -1 to 0, it would actually give you a -1/2 since we're underneath the axis. And so if we were to go from -2 to 0, for instance, if we were to integrate the function from there to there, you would have positive 1/2 here, -1/2 here, which cancel out to be 0. And so I would know the integral from here to here is 0. So that's why I'm finding all of these areas, because knowing the areas under the curve of the function, or the area trapped between the curve and the x-axis, is equivalent to the integral of the function, which is what they're asking us to find here in part A. So if I keep going, this small triangle here has a height of 1 and a base of 1/2. So 1/2 times 1 is 1/2. You divide that by 2 to get 1/4. And notice it's -1/4 because, again, we're below the axis. Then we have another triangle here. It has a base of 1.5, or in other words, a base of 3/2. Multiply that by the height of 3, which gives you 9/2. Divide that by 2, and you get 9/4. So that's the area of this bigger triangle. And then you've got this interesting curve section. So the way we're going to handle this is we're going to look at this entire square. Notice we've got this 3 by 3 square, and I know the area of a 3 by 3 square is just going to be 9. But I don't want that whole box. I only want this section right here. So this 9, what that represents is the area of the whole square. And then I'm going to subtract out the portion I don't want, which is this portion right here. Now, according to the prompt of the problem, they told us that this is going to be the quarter of a circle. The circle is centered right here, which means we have a radius of 3. So the whole circle, if it has a radius of 3, remember the area of a circle is pi r squared. And so since 3 squared is 9, that means the whole circle would have an area of 9 pi. But since we only have 1/4 of that circle right here, the area of this section would be 9 pi divided by 4. And so what you see here is 9, which again is the whole square. And then I'm subtracting out the area of this quarter circle, which would be an area of 9 pi minus 4. And by taking the whole square and subtracting out this portion I don't want, that should leave us with this area trapped under the curve. All right, so to get into the actual problem here, notice that the integral from -6 to 5, which would start way over here at -6 and go all the way to 5, can be broken up into two pieces. So what I've done here is I've broken it up into the integral from -6 right here to -2, plus the integral from -2 all the way to 5. So I've broken that up into two manageable pieces. And the reason I did that is because they wanted us to find the integral from -6 to -2, which is this piece right here. And they told us what the whole integral is. So I know that this piece we're looking for plus this piece right here, which we can find using all these areas, is going to equal the whole thing, which is also equal to 7. All right, so once I've taken the big integral here and broken it up into two pieces, I'm going to substitute. So I know the integral from -6 to 5 is 7, because they gave us that in part A. And that's going to be equal to the integral from -6 to -2, which is the thing they want me to find, plus the integral from -2 to 5, which I can get using these areas that we've shown. So where these numbers came from, we said earlier that if you integrate here and here, the 1/2 and the -1/2 will cancel. That's why you don't see any 1/2s right here. The integral from 0 to 1/2 is -1/4, and that's where the -1/4 comes from. Then integrating from 1/2 to 2 gives me this triangle here, which is +9/4, and that's why I'm adding 9/4. And then plus this little section here at the end, which we've already shown is 9 minus 9 pi over 4. So what these numbers represent is the integral of f from -2 all the way over here to 5. And again, we get that just by accumulating all these areas. So once you get here, we just need to simplify. And I know that -1/4 plus 9/4 is 8/4, which is the same thing as 2. And then I would have 2 plus 9 is 11. So that's all you see here in this next step is taking all these numbers in parentheses and simplifying those down. And then since the integral from -6 to -2 is what I'm trying to find, I need to isolate that. So I'm going to take the -9 pi over 4 and add it to the other side, which would make it +9 pi over 4. And then I'm going to subtract 11. So 7 minus 11 is going to be -4. And that gives me my answer. So it's going to be +9 pi over 4 minus 4. All right, moving on to part B. Evaluate the integral from 3 to 5 of 2 times f prime of x plus 4 dx. So the first thing I'm going to do is break this up into two integrals. I'm going to integrate this piece and this piece separately. So all I'm doing right here on the left side of the equation is rewriting that original integral as two separate integrals. So here I'm integrating f prime of x. I pulled the 2 outside of the integral. You don't have to do that. That's just my preference. And then I'm going to add to that the integral of 4. So if you integrate f prime, the integral of the derivative is going to be the original function. So the integral of f prime is f, and that's what you see here. That 2, that constant, it just hangs out. It's not going to go anywhere. And then we've got to evaluate that from 3 to 5, which means our next step is going to be to plug in 5 to x, and then subtract and plug in 3. And then I've got plus the integral of 4. Well, the integral of 4 is 4x. And again, I need to evaluate that over my interval from 3 to 5, and I'm going to do that by plugging in the 5, subtracting, and plugging in the 3. So that's my next step. If you plug in the 5 right here, you get 2 times f of 5, and then you subtract and plug in the 3, which gives you 2 times f of 3. And then plugging in 5 for x here gives you 20. You subtract and you plug in 3, which gives you 12. And so this part's easy. 20 minus 12 is 8. But in order to evaluate these two expressions, f of 5 and f of 3, we're going to need to go back to that graph that we were given originally. So it looks like if you look at the graph that when x equals 5, your y value is 0. So f of 5 is going to be 0, which is going to cancel out that first term. Minus 2 times f of 3. Well, f of 3, we wouldn't know that unless, if you remember at the very beginning in the prompt, it was actually given to us. So I'm just going to take that value that they gave me and plug that in for f of 3. I'll simplify this down to 8, and here you go. So you got negative 2 times f of 3, which they told us earlier was 3 minus the square root of 5. We've got plus 8, which just comes from 20 minus 12. And so if you distribute, negative 2 times 3 is negative 6. You're going to add that negative 6 to 8, which gives us the positive 2. And then negative 2 distributed to the negative square root of 5 is going to be positive 2 square root of 5. And that gives us our answer on part B. One thing I'm not sure I have mentioned is that I always recommend circling your answers on these tests. That makes it really easy for the AP graders to right away see where you've gone with the problem before checking the rest of your work. It's just a helpful tool. Sometimes students' work can be really messy and the actual answer can be floating somewhere out there in space, and it's hard for an AP grader to search through all that work and find it. So if you circle the answer on the page, that gives us an immediate clue of where to look for the answer, and it helps us kind of work backwards and look at the work that led to that answer. So I always recommend circling it on the AP test. All right, part C. We have a function g, which we didn't have before, so this is new. And it's given by the integral of f from negative 2 to x. And we want to find the absolute maximum of g on the interval negative 2 to 5. Justify your answer. So we've actually, if you have been going through this series, if you remember number 1, when we had to find an absolute maximum on that problem, we're going to go through the exact same process here. If you want to find the max or min of anything, what you're going to do is take the derivative of it and set it equal to 0. So if I want to find the maximum of g, I'm going to take the derivative of g, which means taking the derivative of this integral right here. And if you remember from number 1, when you take the derivative of an integral, the derivative and the integral, they're inverse operations, they'll cancel each other out, and you're just going to be left with f. So essentially, the derivative of g is going to be equal to f, which is what we have written right here. And as I said, if you want to find the maximum, you're going to take that derivative and set it equal to 0. So essentially what we're looking for is anywhere where f of x is equal to 0. So we pull up our graph of f again. And I notice it equals 0 right here at negative 1. It happens again at 1/2. And it happens again at 5. So we're going to list those. And those represent critical values. Those are places where you could have a maximum or a minimum. It doesn't mean you will have a max or a min, but they're possibilities of where you might have those. And then we also have to test endpoints. 5 was already taken care of because f of x equaled 0 there, but we've also got to be sure to include negative 2 because you can have maxes and mins at endpoints. But at this point, all we're going to do is construct a table of values, which is going to look like this. Now, where did I get these? Again, we're going back to these areas that we found earlier. So if you look at your x's, let's say x is negative 2. Well, if I plug in negative 2 to g, and if I'm looking for g of negative 2, what that means is I also plug in negative 2 right here, and I'm integrating from negative 2 to negative 2. Well, anytime you're integrating from one bound to the same bound, you're always going to get 0, so that's where the 0 came from. And then for negative 1, I'm going to plug negative 1 in for x, and I need to integrate from negative 2 to negative 1. Well, looking at our graph, going from negative 2 to negative 1 is this triangle here, which has an area of 1/2, so that's where the 1/2 came from. If x equals 1/2, that means you're integrating from negative 2 to positive 1/2. Well, I know negative 2 to 0 gives me 0. Those two areas cancel each other out. And then integrating from 0 to 1/2 gives me that triangle right there, which is going to be negative 1/4. And then finally, we've already done this work, thankfully. If you go back to part A or B, we had to actually integrate negative 2 to 5. I believe that was part A. And we already found out that was 11 minus 9 pi over 4. So if you go back and look at your work there, all we're doing is accumulating all the areas from negative 2 to 5 that ended up being 11 minus 9 pi over 4. Again, this counts as your justification. This is called a candidates test. You've identified every possible place where there could be a max or a min. You're finding the value of the function at all of those places. So at this point, all we've got to do is find the biggest number, which is clearly going to be this over here. So to answer the question, we say the absolute maximum value of g of x on the closed interval -2 to 5 is 11 minus 9 pi over 4. Again, please be sure to actually answer the question. I can't tell you how many times I've seen students do all the work correctly, fill out the table of values correctly, and then never actually give a final answer. So this is the answer. The absolute maximum of this function on this interval is 11 minus 9 pi over 4. Okay, so moving on to part D. Find the limit of this function as x approaches 1. This is one of the questions I graded, and I can't tell you how many students expected this to be extremely complicated. I think everyone just wanted it to be L'Hopital's rule, if you're familiar with that, just because that's what they expected to be asked, I suppose. But don't forget, on limits, the first thing you should always try is simply to substitute this number into the expression. And so if you just plug in 1 for x, what you end up with is this expression here, which is 10 to the first power, which is 10, minus 3 times f prime of 1 over f of 1 minus arctangent of 1. And in order to figure out f prime of 1 and f of 1, we've got to go back to our graph again. So f prime of 1 simply means the derivative or the slope of this function at x equals 1. So what is the slope, essentially, of this line? And if you just take a look at rise over run, it looks like it's clearly going up 2 and over 1, which means it has a slope of 2. So I would say the derivative of the function right here at x equals 1 is going to be positive 2, which I'll substitute here in a moment. And then f of 1, well, that's just when x equals 1, what's the y value? The y value is 1. So I'm going to go ahead and substitute that. So on the top, I get 10 minus 6, which simplifies down to 4. On the bottom, I have f of 1, which is 1, minus arctangent of 1. Now, you don't actually have to know what arctangent of 1 is. I hope that you do. But if you don't, you could leave this expression right here, and you will get full credit on this problem. But if you happen to know arctangent of 1 is pi over 4, you can go ahead and take that next step. But I do want to be clear that either of those expressions there would give you full credit on this problem. Now, like I said, a lot of people assumed this is going to be more complex, and so they immediately started to take the derivative of the top and the bottom, which is what you would do in L'Hopital's rule. But remember that L'Hopital's rule only applies if you get an indeterminate form like 0 over 0. And notice here, when you plug in 1, we do not get an indeterminate form. This is not 0 over 0, which means L'Hopital's rule doesn't apply here. It's not a correct method to use on this particular problem. So always start with the basics. Just plug in your x value first, see if it gets you an expression. In this case it did, and you're done. So part D turned out to be fairly straightforward. Okay, so that should be it for this one. Again, really common. If you go back and look at previous AP exams, the problem that's similar to this is easy to pick out because it's always going to have a graph that looks something like this. With geometric shapes that you can find areas of, or if you can't, they're going to tell you what the areas are. But there's one of these almost every year, so if you want to go back through previous AP problems, just pick out the one with the graph, and that'll be a problem similar to this one to work through. As always, if you have questions, you can leave a comment on the video, or you can email me directly, and I'd be happy to help you with that. I'll see you soon for number 4.